Let's look at one more example of finding the matrix for a linear transformation. So we know that to know a linear transformation, it's enough to specify the result of the transformation applied to a basis for the domain space. Here the domain space is R2. The codomain also happens to be R2. And these two vectors, 2 minus 6 and 1 minus 2, do happen to be linearly independent, which you can check. And that means that by declaring these two outputs for the linear transformation t, I am determining the linear transformation t on all of R2. So the question is, what is the matrix for this linear transformation? Since every linear transformation does have a matrix, there must be such a linear transformation. But, we know that the matrix for a linear transformation is given by, you just take the standard basis. So for this example, since we're going from R2 to R2, it would be two vectors in the standard basis. You take the results of the outputs of the linear transformation on the standard basis vectors, you use them as columns, and that gives you the matrix that corresponds to this linear transformation. But in this example, we know what the linear transformation does to this particular basis, but this isn't the standard basis. So this trick for finding the matrix A does require the standard basis here, and we don't have the standard basis. So what can we do? Well, if this really is a basis, 2 minus 6 and 1 minus 2, if this really is a basis, then that means it ought to be possible to write the standard basis 1, 0 as a linear combination of this basis. So 2 minus 6 and 1 minus 2. So it must be possible to find A1 and A2 to make this possible. But this amounts to solving the equation 2 minus 6, 1 minus 2 times the vector of our unknown coefficients, A1 and A2, equaling 1 and 0. And then we should be able to do the same thing for the other standard basis vector. So that's going to be 0, 1. And there should be some other coefficients. So I guess I'll call them b's. B sub 1 times 2 minus 6. And b sub 2 times 1 minus 2. And, finding b1 and b2 in this situation amounts to solving the equation 2 minus 6 1 minus 2 times b1, b2 equals 0, 1. And then to solve these systems of equations, we would row reduce this matrix, 2, 1, minus 6, minus 2. But, this is all seeming very familiar. This is actually exactly what we did when we figured out how to find the inverse of a matrix. So, what we're really doing here is solving these two. If we put these two equations together, what we get is the following. We get the matrix equation 2, 1, minus 6, minus 2 times the matrix A1, B1, A2, B2 equals 1, 0, 0, 1. And then to solve this equation, right, remember that amounts to finding the inverse for this matrix, which we know how to do to solve this sort of equation. In other words, to find the inverse here. So this matrix doesn't have a name right now. This is the matrix that we formed by taking 2, 6. Maybe we should name this V1 and this V2. This is V1 and V2 together, right? And over here we have the standard basis vectors E1 and E2. And what we're finding is an inverse for this matrix with the V's in it. So this is not the inverse for the matrix A. In fact, we don't even know if A will have an inverse, but we're looking for the inverse of this matrix with the V's in it. And that's something that we can find. We know how to calculate inverse matrices if they exist, right? You augment the matrix you want the inverse of with the identity matrix of the appropriate size, and then you row reduce. So let's see, let's do second row plus 3 times the first row. That ought to get rid of that minus 6. So 2, 1, 1, 0, and then 0, 1, 3, 1, I guess. Okay, and now we need to use the 1 in the bottom right to eliminate the 1 just above it. So now we can do row 1 minus row 2. And that gives us 2, 0, minus 2, minus 1, 0, 1, 3, 1. And now we just need to divide the first row by 2. So this is going to first row divided by 2, so that's 2, 0, sorry, 1, 0, minus 1 half, 0, 1, 3, 1. Okay, so here's the inverse that we were looking for. Maybe we should call this matrix V, and then this matrix V inverse over here. Okay, so what were we doing with this matrix? Well, remember this matrix V inverse, which should show up right here. This contained the coefficients that turn the standard basis vectors into, or the coefficients that write the standard basis vectors as linear combinations of the basis that we have. Okay, so now what we can do is to find what this linear transformation does to the first standard basis vector. We can write the first standard basis vector as a linear combination of the 2 basis vectors we have. And remember, these were the coefficients for that linear combination. So minus 1 times the first vector, which was 2 minus 6. And then plus this one here, 3 times the other basis vector, which was 1 minus 2. Okay, then we can, now that we have this written as a linear combination, we can use the characteristic property of linear transformations to write this as minus t applied to 2 minus 6 plus 3 times t applied to 1 minus 2. Now we have minus 1 times, and then this right here, this is something that we knew from the very beginning. This is what we had at the start, and that was 3, 3 plus 3 times t of 1 minus 2 is minus 4, 1. And now we can just compute this result. So let's see, minus 3, minus 12, so minus 15. And then minus 1 plus, minus 3 plus 3, that's 0. Okay, so that's the result of this linear transformation applied to the first standard basis vector. And now we need remember our goal is to form this matrix A that's t applied to E1 and t applied to E2. So we just found t applied to E1. Now we need to find t applied to E2. So t applied to E2. We can, first thing to do is write E2 as a linear combination of the 2 basis vectors we have. And the coefficients for that are right here, right? Because remember here we have V times V inverse, and those coefficients B show up as the second column of V inverse. So minus a half and 1. And the vectors that go here are the basis vectors that we started with, which were 2 and minus 6, and 1 and minus 2. Okay, and then we can use the characteristic property of the linear transformation, so minus 1 half times t applied to 2 minus 6 plus 1 times t applied to 1 minus 2. And then again, these values for t were the input data for this whole mess. So t of 2 minus 6 was 3, 3. And t applied to 1 minus 2 was minus 4, 1. Okay, so minus 3 halves, minus 4, so that's minus 3 halves, minus 8 halves, minus 11 halves. And then minus 3 halves plus 1 is minus a half. Okay, I hope I did that arithmetic correctly. And that's t applied to E2. So now we have t applied to E1 and t applied to E2. So now we can put those together to form our matrix A. So minus 15, 0, and minus 11 halves, minus a half. Okay, so fair enough, we did it. We were able to find the matrix A that represents the linear transformation T, but this seems not as efficient as it could be. So let's sort of cast our eye back over what we did. So the first thing we did was we put our vectors, right, the basis vectors that we started with, and we just put them into a matrix and we found the inverse of that matrix, right? Okay, so that's pretty straightforward, but this whole computation step after that, what's going on here? Well, here, right, these are coming from the first column of V inverse. So what's really happening here is it's like we're multiplying this first column of V inverse by whatever these things are, right? If we put these into a matrix, we get 2 minus 6, 1 minus 2. I'm sorry, back up. That's not what I meant. Look here, this is what we want. So these two coefficients, that's the first column of V inverse up here, so minus 1 and 3. But what are they multiplied by? They're multiplied by these two vectors, right? And then added, so it's as if we're multiplying the vector 1, minus 1, 3 on the left by the matrix 3, 3, minus 4, 1, right? And then down here, well, here we have the second column of the matrix V inverse, which was minus a half and 1, times the exact same matrix, 3, 3, minus 4, 1. So, I mean, I guess, so, right, this matrix product goes here, and this matrix product goes here. So I guess what I really want to know now is, what the heck is this matrix? Because this is, right, what we have here is V inverse times whatever this matrix is. So what is this matrix? Where did these numbers come from? Well, if we sort of scroll back through everything we did to look for these numbers, well, those are just the output vectors that we started with. So, if we called this W1 and W2, it looks like this matrix right here, that looks like the matrix W1 and W2. It doesn't look like it, it is that. So to get the first column of A, we use these coefficients to form a linear combination of these columns. And then to get the second column of A, we use these coefficients to form a linear combination of the same columns. But that's what matrix multiplication does, right? Matrix multiplication just takes the columns from the matrix on the right and uses them to form linear combinations of the columns of the matrix on the left. So it looks like what this is W times V inverse, right? And W was just the matrix with our original output vectors, and V inverse is the inverse of the matrix with our original input basis, right? So, that makes you wonder if that's a coincidence or if this is always going to happen. So what would the general situation be? So let's think about the general situation. So this was a very specific 2x2 example. Let's think about the general situation. So suppose that we have a linear transformation, and we know the values of this linear transformation on a basis for the domain space. So the domain space is Rn, so we have n basis vectors to begin with. Those I'm calling v's, v1 through vn. And we have n output vectors, w1 through wn. So if our previous example was right, then what we ought to do is form a vector w, which is going to be w1 up through wn as columns, and form a matrix v, which is going to be, let's see, it has v1 through vn as columns. Okay, each entry in v, or each column in v, since these vectors each have n entries, v is actually n by n, right? It has n rows because its columns are coming from Rn, but also it has n columns because there are actually n vectors here. W has n columns, so it's something by n. But how many rows does it have? Well, the vectors the W vectors, these are the output vectors, they're coming from Rm, so W must have m rows. Okay, so our guess for what A should be was it should be W times V inverse. And W, again, that's n by n, and V inverse, well, V is n by n, so V inverse is also n by n. So if nothing else, this product that we guessed is actually defined. So that's a good start. That's a good start. So let's guess that A is W times V inverse. So how can we check that this is correct? How can we check that this matrix actually determines the linear transformation T? Well, remember that a linear transformations agree if they agree on a basis, right? So if we can show that the linear transformation and multiplication by this matrix agree, so if we can show this, then A is the matrix for T. And when I say the matrix for T, that means that T of V is equal to A times V for every vector V in Rn, right? So they determine exactly the same transformation from Rn to Rm. Okay, so how can we prove this? Well, I mean, what we're going to have to do is take these basis vectors V and multiply them by A just to see what we get. But you can see that the first thing we're going to run into is we need to know what is, that's a W, what is V inverse times one of these V vectors, right? That's the first thing we're going to need to know. So let's figure that out. Well, what do we know about this matrix V inverse? We defined V, right? V was the matrix that has just the V's as its columns, like this. Okay, so if we took V inverse and multiplied by VI, right, what would we get? That's what we're trying to figure out. Well, let's call this X. In fact, let's call it XI. And let's see, the problem is we don't know very much about V inverse. We know a lot more about V than we do about V inverse. So to turn this equation that we don't know much about into an equation we know more about, let's just multiply on the left by V. If we multiply on the left by V, we get V inverse times VI equals XI. Remember, we don't know what XI is yet. But V times V inverse, that's just the identity matrix of the appropriate size, which is size n, times VI Oh, I'm sorry. On this second line, I forgot to write my V matrix right there. Okay, and then the identity matrix times VI is just VI, of course. So VI is the matrix V times this unknown vector x sub I, right? And so we have V, the vector VI is the matrix V, which, right, is like this. Its columns are just all the V's, times x sub I. And we want to know, what is x sub I? This VI that we're looking for, it shows up. It's one of the columns of this matrix. So we could choose an appropriate vector to make this product, to force this product to choose the ith column, right? All we need from this matrix product is to pick out the ith column. But we know what vector does that. To pick out the ith column in a matrix, you use the ith identity, or the ith standard basis vector, right? The ith standard basis vector is the standard basis vector that has a 1 in the ith position, and so multiplying by this matrix will pick out the ith column. We've seen that before. So the x sub I here is actually e sub I. Okay, so now let's go back to where we came from. That was up here, right? We wanted to know what was V inverse times V sub I. We named this x sub I, but what we just figured out is that's actually the ith standard basis vector, right? So now we know what V inverse times V sub I is. Okay, it's the ith standard basis vector. So why were we looking for that? That was because we had a guess for A, right? And we wanted to check, what do you get if you multiply A by these basis vectors VI? So now let's do that calculation. I'll do it in red right here. So what is A times V sub I? Well, A is the matrix W times V inverse, right? And we're multiplying that by V sub I. Now, this first product, remember matrix multiplication is associative, so we can throw parentheses in here. And the product in parentheses is what we just worked out. That's the ith standard basis vector, so E sub I. But what is W times E sub I? Well, multiplying by E sub I just picks out the ith column. What is the ith column? Well, it's W sub I. And what is W sub I? W sub I was our name for the result of the linear transformation applied to V sub I. Right? So what we found is multiplying by A does the same thing to V sub I as the linear transformation. But that means that A is the matrix for this linear transformation. So this formula that we guessed is actually right. Okay, it's pretty nice. It takes a little bit of work to check. In particular, dealing with V inverse is a little bit tricky, but it works. That's pretty slick. So here's what we worked out. Right. If we have a linear transformation from Rn to Rm, and it's defined on a basis, and this can be any basis, doesn't have to be the standard basis for Rn. And if you know the outputs of this linear transformation for these basis vectors, then form the matrix V and W, just by cramming all these things as columns into a matrix, then the linear transformation is given by multiplication by W times V inverse. Right? That's what we just proved. So that's pretty slick. So let's look at an example. Let's find a matrix for the linear transformation from R2 to R2 determined by these two values. So since we're coming from R2, a basis would have two vectors in it, right? So here we have two values for the linear transformation. These two input vectors are indeed linearly independent, which I'll let you check. So to find the matrix associated with this, remember all we need to do is find the product W times V inverse. So for V, that's the matrix whose columns are at these inputs. So 2, 3, minus 1, minus 2. Now we need to find the inverse of this. So to find the inverse, we have to do a row reduction. There's no getting around that. course, we could ask a computer to do it, but I can't be bothered at the moment. So 2 minus 1. Now this is actually a little bit unfortunate. We're going to get some messy fractions. So I'm gonna play a little trick, which is you don't have to always use this number to eliminate that number. I can use that number to eliminate that number first. That works just as well. So what I'm going to do is do row 2 plus minus 2 row 2. So this is minus 2 row 2. So that's going to give me 2 minus 1, 1, 0, and then row 2 minus 2. So minus 1, 0, minus 2, 1. Now I have a 1 here. I can use that minus 1 to eliminate the 2 above it. So row 1 plus 2 row 2. So that's, let's see, 0 minus 1. So let's see, row 1 plus 2 row 2. So minus 3. I hope this is right. And then 2 minus 1, 0, minus 2, 1. And now we can interchange the two rows and also take their negatives. So when we do that, here we get the identity, and in our augmented part we get 2 minus 1, 3 minus 2. Okay, so here's V inverse. All right, step 1 complete. Now we need to write down W and then just do the matrix product. So W is the matrix whose columns are the output vectors, so 3 minus 1, 4, 4. Okay. Something that maybe wasn't obvious when we were proving things is that the columns in V and the columns in W, they have to be in corresponding order. Right? That was in the proof, but I didn't really point it out. So you have to keep things in the order that you started with. So here's W. So then A is W times V inverse. So 3, 4 minus 1, 4 times 2 minus 1, 3 minus 2. So this is, let's see, 6 plus 12 is 18. And then minus 2 plus 12 is 10. And then for our second column, minus 3 minus 8 is minus 11. And then 1 minus 8 is minus 7. Okay, so I'm not super confident that I didn't make any arithmetic mistakes, but I hope you get the idea. So this linear transformation that we started with is actually determined by this matrix, which, I don't know, these numbers seem so big that it seems implausible. I'm tempted to check. So let's actually take our matrix and apply it to these two vectors, or multiply it by these two vectors. So we've got 2, 3, and minus 1, minus 2. So we're going to take both of these and multiply them by the matrix A. So 18, 10, minus 11, minus 7. And hopefully we get the outputs that we were supposed to get. We should, if I didn't make any arithmetic errors, which again, I'm not too sure about for some reason. So 18 times 2, that's 36 minus 33, so that's 3. And then 20 minus 21, that's minus 1. And then 18 plus 22, so that's 4. And then minus 10 plus 14, so that's 4. So I remember this one. Is this one right? 3 minus 1? Ah, yes, it worked. So what do you know? Math works, as long as you do your arithmetic correctly.